to the PowerPoint. And essentially, I want to start with a disclosure at the beginning, because I'm reviewing a few Gunfire systems, which are very well known to exist because they are publicly documented and widely advertised. But some of their details are trade secrets or they are out of control. So they are sensitive. But the talk is totally based on publicly available information. This review is essentially analogous to your shopping for a computer before getting one, because you're comparing general features like RAM, storage, speed, software support type of issues, and then looking at interfaces. You're not really learning the internal workings or how to build a computer by just reviewing what's available out there, namely in terms of sales brochures. So in the same way, this review is conforming with applicable regulations because it describes the systems macroscopically, general features, basic principles, and so on, and describes nothing microscopic, and certainly doesn't let you know how to build one. And its contents, all the photos, videos, and system features that I will show have been publicly documented. And in fact, I'm citing all the references they've been taken from. And that way, I both give credit to the sources as well as, letting you know that they are out there in the public domain. So the disclosure that I did already was done. I'm going to talk a little bit about the motivation and enabling technologies, references, a list of references where everything came from, and then kind of simulated demos of system operations. Then at the end, I'll just talk about the physics of gunfire detection and localization. Then we have questions and answers. So if we start with the introduction here, the initial motivation came from military sources, basically because they had severe requirements for, and that was the prime driver as well as the prime funding source for these systems to be developed. And that was the need to reduce the number of friendly soldiers that were killed by enemy snipers. So in this context, sniper detection and localization system is against some kind of a marksman who is shooting at people, friendly people from concealed and distant places. Later motivation for non-military grade systems came from the needs of the law enforcement agencies, where they essentially trying to, of course, reduce civilian killings in the United States. And in this context, a shooter, not a sniper necessarily, includes criminals that are committing assassinations, robberies, gang fights, and so on, or deranged civilians that are committing mass murders at various congregations. The reduction to practice came and was enabled by the proliferation of miniaturized digital hardware and also good software to go with it. Of course, there was a spiral implementation for all of the systems as they were integrating lessons learned. And all of the non-military systems really are downgraded, I would say, or at least morphed sniper detection systems. I was interested at the beginning on who were some of the famous snipers, and actually infamous more to the point, because I wanted to cite people that really did some really bad acts. And when I Googled sniper definition, I got all of these different definitions over here that you see, but the key things were from cover or concealed place, long ranges, and marksman type of thing. So at the bottom, you see that a sniper is typically a marksman shooting at people from concealed and distant places. Some well-known snipers, and I got to them, actually, I was trying the word infamous first, because I wanted to get to the bottom line, to the bottom row of this list. And there was no such thing. There were no infamous snipers. There were only famous, best, top, deadliest. And then I found finally the bottom row by putting in criminal snipers, which I don't know if it says something about how the selection process works when you Google something. Some famous names, not necessarily the most famous, are Tim Murphy, that was essentially an American Revolutionary War hero, a Russian, or rather Ukrainian woman, Lyudmila Pavlichenko, that actually shot a lot of Nazis from long distances, Chuck McWeeny, that was in the Vietnam War, and more recently, Chris Kyle, that was in the Iraq War. We have then several Hollywood characters like Edward Fox in Jackal, you know, and Tom Berenger is Sniper. And then the bottom row is Lee Oswald, James Earl Ray, and a guy who apparently raised havoc in Iraq with the American soldiers. His name was Juba. And I don't know if this figure, is this photo over there is actually a photo that was taken from a distance or just a kind of notional representation of him. But he was probably the main and prime mover for the development of some of the systems by the Allies that came down to practice eventually. So my sources of the presentation material included a lot of papers, videos, and just narratives from the internet. I had about 25 different relevant sources, but eventually I got some things from the ones listed here. And you see each one of them has a red number next to it. That's a number from my list of references. And then each picture or video, or sometimes text that I show, has one of these numbers, which says that, hey, I got it from the internet. It exists out there. It's not anything that is not public information already. Okay, and these references include videos. So one of them, let's see, is for a French system, a US system, and then both of these are military. This one over here is commercial, and it's again video, and the rest essentially were sources of photographs, except for the last one, which is also another video. And then I have some personal animations that I did with MATLAB. So let's see, the publicly documented features and operation of representative systems. If we look at the French system first, PILAR V, it's called, and it is based on this. So at this point, what I want to do is stop sharing this and choose something else. I'll show you a video. So I was going to explain the French system, but somehow my videos went to the US system first. So I'm going to explain what I was going to explain later about the US system, and then I'll come back to the French system. So essentially, you can see my PowerPoint now, correct?
Yes.
Okay, so the video was kind of went through everything fairly fast. So the thing is that now, but it's a small image that you see correctly.
Right, just hit slideshow up on top there.
All right, there we go. Okay, so the video went pretty fast. So essentially I wanted to point out a couple of features by borrowing some snips from it. Over here, the captain was talking about the system, and you know, they can have many antennas in these places, and one of them at the top is holding a boomerang. Then the soldier, the US soldier was talking about it, and there was a boomerang near him. This guy was assembling it. In this particular case, he is putting all the microphones on the array, and that's how it's built up. And then over here, he's placing the assembled array into a pole that essentially just keeps it up. This is for perimeter defense, but the whole thing, both this boom, as well as the box down here, which contains this, can be mounted in the back of a vehicle, and I'll show you a picture later. And then this is the screen that announces the bearing, like azimuth is 74 and range is about 187 meters. All right, so essentially, and then the boomerang in that mode is used over here in order to protect buildings from snipers. And by the way, when we say protect from snipers, a shot has to be fired before the sniper is detected. So you hope that he misses with the first shot, and then everybody hears it and ducks. Or at war, when somebody's shooting at a vehicle, if he misses the first shot, let's say, then everybody knows where the sniper is and starts firing in that direction, or they know best how to hide behind the vehicle on the opposite side of where the sniper is. So over here, we see the perimeter defense. Here's another picture of the boomerang that came out of Wikipedia. And by the way, here are the numbers that refer back to my list of references in the page that I showed you. And then, so here you see now the vehicle mounted systems. Here is a display that can be on a laptop, namely, you can hook these systems onto the laptop or desktop or even this iPad, as this soldier down here is holding, so that you can have some kind of a display that shows you the analog of this part and shows where your sensor is, and then shows where the sniper was, distance and bearing. And sometimes it contains a map where you may have a sensor here and the sniper was at the red spot over there. And here is an in-theater type of implementation where there may be a central command center that receives sounds from and signals from everything. Here you have a convoy of vehicles, each one of them carrying one of these systems. This soldier is carrying one on his shoulder, which is in one of the references, a man-wearable system, they call it. And then you have a display of this whole area of this entire valley over here and the river along here, and where the sniper is firing at the people, at this convoy. Okay, then next slide. So the typical scenario when you have a vehicle mounted system is that, okay, here's the plan view of the vehicle. Here is on one of the sides, it's not clear on which one usually, is one of the sensors. The forward direction signifies the 12 o'clock position, and then everything is referenced in the military sense to some direction on the clock. And you can see over here that the visual display has LEDs from 1 to 12. And then there is what we saw earlier when Captain was talking, there's an azimuth and range displayed here. So the assumed scenario in this case is that the sniper is here, fires a bullet. This is the red line that signifies the bullet path, and he's about 300 meters away. So the sensors pick up the signal. Somehow they communicate it to this box where it gets processed. And I don't know where this box is normally located, but I'm guessing it's somewhere near the driver. And then the system gives both the visual, the LED light, as well it makes an announcement from the speaker, something like shot 1 o'clock, 300 meters. Now this is the non-military version of one of these systems. And this particular is called a Guardian, and it's made by a company called Shooter Detection Systems. It's a US company. And essentially this is totally different, not in appearance anyway, because it is meant to be for generally enclosed spaces like department stores, interior airports, large shopping centers, maybe stadia in some cases, but there are also the outdoors versions that can be installed on top of buildings, telephone poles, and so on. This in particular that is suited for corridors has microphones, 2 microphones over there that you can see. It's flush mounted to a wall. And then it has 2 IR sensors that are pointing in opposite directions so that you can get also a cue about that when a shot is fired in that particular corridor. By the way, again, all of this wording and the pointers and so on came from reference 4. It's out there in the internet. So with these systems, typically you'll get on a computer the display of the floor plan of whatever area is protected. And then, of course, you can have additional things that can integrate cameras that are maybe installed nearby that can show you a view of the shooter on a magnified version of this floor plan. And of course, these can be integrated in law enforcement systems that are remote so that they can send some first response, first responders to the site. All right. Now I'm going to go back to the French system for a moment. And to do that, let me first go out of here. Oh, I can actually just back up, can't I? Yeah. So this is where essentially I chose the second tab instead of the first. So if I go back to this and acoustics, by the way, you see this right now, what I'm choosing? I don't need to stop sharing, correct?
No, correct.
Oops. There.
You just have to.
And now, is the sound on? We'll
Just
find
no.
out.
We're not seeing a video here. We're still seeing the PILAR V French military system.
Okay, so this one, stop share for a moment. Let me go and choose it. And I'll share my entire desktop. Sure. There is Peter looking at us. All right, so I'm going to choose this. Take the whole screen. Now, you said the sound is okay down here, something that I should do. Well, let's play it. And the nice thing about this.
No sound, Tony.
No sound, okay, is that it has no narrative, just some music. So I thought I had mastered this thing, but I guess I have not. Tell me again what to do to get the sound, Steve.
On the bottom left, when you share it.
When you're sharing.
When I start, so stop share first and then share again.
And now, when you click on the thing you want to share.
It is checked.
Okay, now look on the bottom, you see on the left.
Okay. Maybe I should choose just the clip itself.
If it's only music, we'll hum.
I don't know what I'm doing about the music over here. Well, the music is not that, it's the kind of long ranger music, you know, that essentially when you do something with that galloping and, all right, maybe I'll be the narrator over here and instead of the music. Okay, so you have a convoy that is, oh, by the way, all of this is simulated with a few video clips in. And you saw already one version of, okay, here is one version of the French system, which is filtered, that has fuzzy kind of looking things, blends into the environment well, and so on. It has 4 sensors, 4 microphones. And here we have the convoy moving somewhere, from somewhere, and it's escorted by a helicopter. And as it enters into some kind of a facility, a sniper shows up in the, here's a vehicle with the system on it. Another one, and a sniper that goes and fires at them. And at this point, essentially, the waves were picked up by the array that does the processing and sends the signals inside the vehicle where somebody monitors a little screen that goes and pinpoints the location of the shooter, at least the direction, like on the clock. And then you can see over here his hand where it's about to launch something, and essentially sprays the sniper with whatever it is that in high energy beam over here. And that's the happy end of that, maybe. Now, the helicopter is moving in a similar way. Here's a sniper that is firing at the helicopter. And again, an acoustic wave is emitted. And you can see here the growing circles, which essentially imply it's a supersonic bullet, and it has a shock cone behind it. On the helicopter, the signals are picked up by an array of sensors that look like this. And essentially they're nicely shaped to take the helicopter environment. They're on both sides of the vehicle, and there are multiple of these. Again, you got over there the bearing to the sniper, and then the helicopter can fire back. So, and that's the end of that. So I'm going to go back to my PowerPoint right now. Now, I forget if I was sharing. Do you see my entire desktop?
No, just the one screen with the acoustic stuff on it.
Here, go back to my my desktop. Get the PowerPoint forward. Okay, so
just share again, please, Tony.
Sure, that's a PowerPoint. Okay, so essentially, here I was, again, you already saw this, the sensor. This is a vehicle that is from another reference that shows the sensor mounted in the back, the helicopter with sensors on both sides, and I should have increased. Can you see the PowerPoint now?
Perfect.
Okay, and so essentially, we saw the features on the helicopter as well as the one on the vehicle. And this is the two processes that we went through. One where the sniper fires against the convoy, it was picked up and somebody fired back at him. And here where he fired at the helicopter and he was fired back by the helicopter after being detected. A civilian variant for law enforcement of that system, the French system, is shown here, or partially shown here, in the sense that it has many different manifestations. For example, it comes in single sensors that can be integrated through, again, coherently processed. And they can use suction cups at the end of tripods so that they can be placed everywhere, on a balcony or whatever. They can be placed on top of police cars or strapped to telephone poles. And they can be essentially, then again, combined. The signals are combined so that eventually you get some kind of a solution by which essentially shows probably where the shooter is over here, so don't stand there. But also, from what I can see here, high risk areas, medium risk, and low risk. What this probably means is that if you're going to approach the shooter, from up here, it's safe. Here you start getting orange, and therefore from the sides, it's a little more dangerous. And if you're across from him, you're visible and all of that. So in this system, like many others, and typically like all the US systems, can be worked, can be installed on a cell phone to a desktop kind of device. Okay, so we did these already. Okay, and now we can talk a little bit about the physics. And for this, I started with a few analogs because I didn't know if we had some non-engineers amongst us. So if you are to comprehend the muzzle blast wave, which is spherical, think of it a little bit like a two-dimensional version of the circular waves that you see on water when a pebble or anything is being dropped on it. Then when you get a traveling bullet, you have a moving source that disturbs the surface of the water continuously. So you get a Mach cone behind it. Actually, this is not a Mach cone, it's a Kelvin cone. There are two types of wave, the phase velocity and group velocity, and the Kelvin waves are slower. So, but I'm not going to delve too much on that. The important thing is that the duck is living, the Mach 4 duck over here, is living a wake behind it, a triangular wave. If we go to 3 dimensions, these circles become spheres. So here you see this is from the Science News, you see a pistol fired. So there is a big circle which is centered at the muzzle. That's the speed of sound circle that is going away from the muzzle, and at all times is centered on the muzzle itself. As the bullet, however, is moving forward, it's a source everywhere that it is because it's pushing the air out of the way. So there is a bunch of circles over here that you see that are moving to the left, following the bullet. Now the bullet is inside the outer circle. That means it's a subsonic bullet. Therefore, it makes no shock wave cone behind it. On the other hand, this round over here is going faster than the speed of sound, therefore it forms a shock cone. And actually, if we are going to see all the features combined in one shot over here, this is a Schlieren photo of firing of a supersonic bullet. So you see the mass injection region. This is kind of the local gun smoke and flash and so on that you get when the round is fired. Then you see the path of the bullet. You see the muzzle blast over here, which, and then I just kind of interpolated or extrapolated to the outer part of the sphere. And the shock wave is tangent to this sphere. And that's the typical characteristics of a supersonic round. So what do we need in order to localize the sniper? We need to essentially determine where the sphere is of the muzzle blast, if we can get to measure it, or we have to determine where the cone is. Define it in space, that is. If you define the sphere in space, you know where its center is, therefore you know where the sniper is hitting. If you define the cone, all you know is where the axis of the cone is, but you don't know where the cone started because it constantly grows as it goes away from the sniper. But that is still by itself is very, very important information because that cone will axis will eventually go through the sniper muzzle. And that sniper has to be standing behind a rock, at a window up in a building, or so when you actually integrate the information, you draw that axis, you find out where it intersects plausible positions for a sniper, and you've got it right there. So, but the common practice is that both of these pieces of information are coherently processed so that you get a more robust solution. That's my phone, and it shouldn't be ringing. I'm going to shut it. Okay. Oh, yes. So over here now, essentially, I wanted to plot and then animate. Yeah, I have a simulation here, as you can see. These key characteristics that I described before. And there are 3 categories over here. A blank bullet, namely there is no slug that will travel. Or think of it as a cherry bomb, maybe, which is just the point source that is not moving. A subsonic bullet which is over here, and then a supersonic bullet. When you have a cherry bomb that goes off and it's stationary, then as time goes by, it produces these blue circles that are going away from the center. And of course, at any given time, only one of these circles exists. And when the simulation stopped over here, you have the red circle. That's the outer limit, let's say. And or over here, that is the muzzle blast wave, not the muzzle blast, I mean the cherry bomb wave, as you see it sometimes later. Here you have a subsonic bullet that started in the center. It makes a circle at any given time. So the outer circle corresponds to the point, to the time point that the bullet was fired. But as it moves to the right, it generates new circles, which are always centered on the bullet itself. So at the end of the simulation, this is the picture that you have. The muzzle blast wave is out there, but the bullet hasn't caught up with it. It will never catch up with it because it's subsonic. And then the third one is where you have a supersonic bullet, which essentially pulls all of these circles out. And that's why you see this. And therefore, at the end of time, at the end of simulated time, you get this picture where you see the muzzle blast circle and the shock cone. Now, if I can, okay, I'm going to go out from this for a minute and this show so that I can pick up this. Oops, now first I have to share my entire screen. Stop share, and then share, and then go to the entire screen. I am sharing the computer sound. Now I know about that tab. So can you see the entire desktop right now?
Yes.
Okay. So here we're going to see the time sequence of that. So as the cherry bomb went off, you saw the blue circles expanding outwards, and then you have just the last circle that we saw. Now we go to the subsonic bullet, which is moving to the right, meeting the circles which are following it drag to the right as it moves. And finally, the supersonic bullet, which is doing the same thing. It drags the circles behind it, but at the speed higher than the speed of sound. That's why you get the cone. And even though each circle may be of low intensity, right on the shock cone, you're actually getting the superposition of many spheres. And that's why, regardless of distance, or at least in the first maybe kilometer, 2 kilometers or whatever, that crack from a shock cone is always very audible, while the muzzle blast is going down like 1/r squared, and that makes it weaker and harder to detect. All right, so going to actually, I'm not going to go back to this, so I closed it. So now I'm going to.
So is it true what you're saying that there are two sounds that are coming from that supersonic bullet? First of all, there is the muzzle blast sound that emanates from where the gun was. And then there is the sound of the bullet as it rips through the air, which means that since it's traveling faster than the speed of sound, if the bullet passed by you, you would hear it after it passed by you from its motion through the air. And then at a time after that, you would hear the crack from the firing of the gun.
Yes. And we'll see some of those features in the last simulation that I have, which is a couple of slides later, where also I have inserted a sensor somewhere in the vicinity of one of these. Do you see now again my PowerPoint screen?
Yes.
Okay. So now the question is, I'm not going to have any more math or something, but all I want to say, how do you determine where the sphere is and where the cone is and so on? And again, I'm doing a couple of two-dimensional things first, and then we go to 3 dimensions. So you think of them as the projections of, as the projections of the 3-dimensional space objects into the 2 dimensions. From basic geometry, we know that if you have any 3 points, they define a triangle. And then, of course, every triangle is inscribed in a circle. And if you drop perpendiculars to any 2 sides, to the middle of any 2 sides of the triangle, the lines will intersect at the circle. Therefore, if you have 3 points in space, you define the circle, period. The same way, if you have a wedge now, which is kind of the 2-dimensional version of the cone, you have a couple more parameters over here. You have, I guess, the center, which is, in this case is the apex. So you have 2 variables over there, x and y0, and the radius is over here. So in addition to the apex, you have an azimuth angle, which is the orientation of the wedge axis with respect to one of the 2 axes, which here they got flipped, as you can see. I meant to put the x here and the y there, but for some reason they got screwed up. And then there are many different cones that can have the same axis, but they have different cone angles. Therefore, you have a total of 4 parameters for the cones. So you need, in 2 dimensions, you need 3 points to define a circle, and you need 4 points to define a wedge. If you go to a 3D geometry, now, in addition to x, y, and the radius, you also have a z direction, a z coordinate for the center. Therefore, you need 4 points to define the sphere. And if you look at the cone equivalent of the wedge, you have the same things, the x, y, 0, but also you have the 3rd dimension, z0. And then in addition to the azimuth that we had over here, we have an elevation angle of the axis with respect to the xy plane. So 4 points to define the sphere in 3 dimensions, and 6 points are needed to define a cone in 3 dimensions. Okay. And now there is the next step where, obviously, when you're dealing with gunshots, this sphere is not sitting there, and you will never be able to put 3 points exactly on one sphere. I mean, the points are where your military vehicle is and so on. However, what happens while in fixed coordinate system and shapes, you have x, y, and z's. In the time varying systems with traveling wave outwards, you also have the additional variable of time. And essentially you can combine, if all the sensors are coherently processing, essentially it's like monitoring the same number of fixed points as required to find the sphere or the cone. So that's a little bit of a jump, but that's all it means. Your sensors can be almost anywhere, and as long as you have the same kind of time code, time domain kind of axis on all of them, you'll find a solution for it. So now this might answer the question a little better, Steve, although all I said was yes. Here, essentially, I chose a scenario where we have a supersonic bullet again. The sniper is at this 00 point, the yellow spot. He has fired the gun, so the bullet has traveled up to here, some distance from the sniper, but it has nothing has touched this sensor yet. And by a sensor here, sometimes I use it interchangeably with array, which means it's a multiple microphone device, okay? It has N microphones. So at this point, there is no acoustic data that was acquired. In the second one, we have event 1, which essentially, again, the sniper is here, but now the shock wave has gone past the array. Therefore, each one of the individual microphones on it has acquired something at time T1 corresponding to the passage of this cone past the sensor. And then event 2, this is kind of distinct in the sense that it happens at a different time, but it has the same actually physical 3-dimensional coordinates X, Y, Z. Same sensors, but different time. But what this means is that here you got N data points because the shock wave went by, and then the blast wave is going by, you get another N data points. So you have a total of 2 N data points, and depending on how many sensors you have, you can get a solution if there are enough, and you can get a much more accurate solution if you have many more than you need. Okay, so, and let's see. I can probably play that one just so that you can see what it looks like. Stop share for a minute. Okay, and then I'm going to my desktop where I will choose this thing. Create and share screen. I'll share my desktop again. And you'll see a figure over here. All right. All right. So the sniper fired the bullet, no acoustic data yet. Then the bullet moved further to the right until the cone passed the sensor. And then in the third case, until the muzzle blast passed the sensor. So because we have defined a circle here, it means that its radius points back to the sniper. And also, by defining the cone, we know that the axis goes through the sniper. So this is a pretty robust solution compared to a single one that you might have gotten if you had only the muzzle blast, let's say. For example, if you have a subsonic bullet, there's no cone. So you have to rely only on the muzzle blast. And in that case, you have to have either a very good signal. Yeah, the muzzle blast goes on down like 1 over R squared. So if you're far away, there's so much clutter that you may not have enough signal to noise ratio to actually do the processing required for a good solution. But if you have 2 of them, so that one is pointing this direction and another one is pointing in that direction, then that's another way to get an answer. So I'm not going to show this again, so I'm going to go away from it. Okay, you see my desktop, right? Do you still see my desktop?
Yes.
Okay, so I'm just going to go to this and return to my PowerPoint over here and go to the next slide. So there are generally, you see the PowerPoint and you hear me, right? I want to make sure.
Correct.
Okay, some limitations are, one of them is a distance because they attenuate the muzzle blast very rapidly and there is less impact on shock wave. I mean, even the shock wave eventually will be reduced. Actually, the bullet will hit the ground at some point, so there will be no more shock wave or anything else. And then there are silencers, which essentially can reduce or eliminate the muzzle blast, right? The muzzle blast, I meant to say there, beyond a certain distance. So the circles that we were talking about become useless, but they have very little effect or no effect on the shock wave. So essentially that one can still be used to get some information. But these are some of the type of limitation you have, in addition to general SNR project problems that you may experience, because there are many other sources that essentially can swap your useful signal. Okay, so we got a little bit about the physics about that, and I want to say a little bit, I really presented to you very basic stuff. This is high school geometry, or it was college 101 physics and geometry or math, let's say. But there's a lot more. There's a lot more to this. And if you want more details, You know, you can go to a patent and a paper that were written about the Boomerang, for example, the US system. This is these are the true references. And, you know, in that one, you see essentially a lot more math, first of all, that defines how things get done. And then you see a lot more about other physical features, like what happens when you have a decelerating subsonic bullet. You know, the shock cone is no longer a cone. It's kind of a rounded cone over here, because as the bullet slows down by the air friction, you know, the cone angle becomes larger and larger. It's like opening an umbrella, you know. It starts very sharp as a cone, and then when you open it, it has a much more rounded top. So notice that this is from 2001, this is from 99. There haven't been any significant things after that other than sales brochures. And the contents of both of these are less flashy than contemporary videos and PDF files that you'll see. But the detailed discussion of physics, algorithms, and system architecture is a useful thing to do that I didn't even try to touch over here, because, you know, some of it may be sensitive, even though it's described there, and some of it is not described there altogether. I suspect that all of these systems, not just this one, have undergone significant improvements since they were first appeared as the young systems, while now they represent well-matured technology and systems. And they've been substantially upgraded, especially using Iraq word lessons learned. And a lot of this has been done quietly, so I don't, nobody knows any publicly available information on the additional improvements in algorithms and things like that that may have been used. I think this is the last one, so ready for questions. Thank you very much.
If I was a bad guy and I was looking to defeat these systems or to mitigate them anyway, if I used a device with a slow-moving projectile, that would be the most appropriate device to use in this circumstance, correct?
By slow, you mean subsonic?
Whatever the definition of slow needs to be, correct?
Yeah, if it's subsonic, there's no shock cone, therefore you cannot get the shock cone. You can get the axis of that cone. You have to rely on the muzzle blast. So if you manage to wipe out the muzzle blast, then you have low probability of detection.
So a slow-moving projectile would be one method of defeating this acoustic system, correct?
Yes.
Now, what about something that is used like a mortar, where there's a high parabolic arc? These things are ineffective for that as well, correct?
Well, it will be muzzle blast only. Obviously, the trajectory over there of a mortar is a ballistic sort of very high arched thing. So getting an axis is not going to get you any useful information. And when it just falls, I don't think it ever is supersonic. So you are only relying on a muzzle blast at that time.
I don't think of a mortar as the sniper weapon.
No.
I mean, a sniper is a guy with a scope. And he's
but I'm thinking of peripheral defense and things like that. You're right. But when they talked about perimeter defense and what have you.
What about robo snipers? Can you make here we're thinking kind of defensively. We're down on the road and they're sniping at us. What about flipping it over and we're sniping at them?
That's what the Israelis used to kill that Iranian recently.
Okay.
Iranian nuclear physicist.
Mm.
There is actually a system, or maybe there is, but there is at least a video, like the French video that was mostly animated, simulated and it was, I think, generated by Toby Hanna Camp base. I have a video for it that you can see. Actually, I can show you if you want to see it, if we have time, that is. But yes, they claim that there is such a system that essentially it's like a robot that is going in front of the convoy So it's the noisy part. It gets fired first and then it fires back. But there is a man in the loop so that, it can avoid firing at the wrong guys. Make sure first that it gets fired at by something unexpected and then fires back. So it has a machine gun at the top or something.
Well, in terms of relative value, don't they use force multipliers where the force is one soldier with a rifle and a bayonet, and you look at any weapon and you say, well, how many soldiers with a rifle and a bayonet is this worth? Whether it's a cannon or a nuclear bomb or a detection device, how much does this act as a force multiplier? It could be 10, could be 20. I don't know what it is, but isn't that how they figure out the value of these things?
I'm not familiar with that kind of information at all.
I remember 15 years ago, maybe slightly more, when drones were pretty new. One of the issues was you're driving along a street and there's a building ahead of you, and presumably snipers or others are behind the building, and so you can't see them. And so Raytheon was building drones that would go up and look ahead of convoys and look on the back side of buildings, rocks, whatever, to see whether there were people there.
But that's a different problem, John, right? That's just like having a spy or something.
Well, that's correct. But the problem is, which is similar with a sniper, is that you can't see them from your perspective where you are because they're behind something, or maybe there's a little hole through a wall. But if you can get behind the wall, in some cases, it's beneficial. Anyway, it's just one more option that's out there.
Yeah,
Oh, yeah.
with respect to that, John, remember what I mentioned about the axis. The axis will draw a line which will go through the hole in the wall, and eventually it points at where the sniper wants. Now, if he moves to the right somehow from the hole, so that the 3-foot thick wall is protecting him, then he's immune to any return fire, regular fire, let's say, not the big howitzer that will fire at him. But he cannot be behind the building. He can hide after he fired the shot behind the building. But at least you will know where he was when the shot was fired. That's the key thing. Right. Then another thing, because you mentioned drones, one of the clips that I came across was describing, it was a TED Talk-like presentation, and described a system which actually was a swarm of little drones that were kind of released either individually or in big clouds. And essentially each one of them was a quadricopter, tiny one, but it had one shaped bullet in it. And they programmed to go and find a person and, neutralize that person. Yeah. It's amazing what they are doing these days, but I'm not familiar with any of the details other than what's on the internet that any one of us can see.
There was a Michael Crichton book 25 years ago, maybe, that talked about these nanotechnology was actually what he was talking about. It's similar stuff.
Yeah. Well, according to this guy, and probably they have some sort of prototype, but he was presenting a simulated kind of scenario where he called it the $1 billion system because it was a big airplane that actually released this big swarm that essentially fought the war, because each one of them had a bullet and each one had a designated target, somehow. I don't know how.
Harry Bruce Perlin?
I didn't hear that. Did someone ask a question?
John, are you speaking to us or you're talking to somebody else?
I think he's left his desk.
Well,
I think
he's left
the
his
answer to
desk.
that, Peter, is probably.
Yeah, or yes, one of the two.
Tony, what happens if, say, there were 5 snipers or 3? Can the system be overwhelmed by too much data?
I don't
Or
know.
if there's a firefight going on and you've got a couple of snipers? So
Yeah, I don't know the answer to that, but I would presume that, you know, because essentially, ultimately, the signal that you receive, that the microphone receives, is a spike. One spike, sharp spike, is a crack of a supersonic, if you have a supersonic bullet. And then later on, there is a less well-defined, less sharp peak, that is the muzzle blast. Now, if you line up all of those, if you have somehow perfectly timed snipers, you know, so that they can all fire a shot and you can overlap their shock waves, it's going to be messy. I'm guessing, I don't know. But the developers of these systems have encountered some such lessons learned, and I'm sure they are doing something about it, but how much, I don't know.
Tony, can you identify the specific weapon that's being used in terms of caliber and type of gun it might be from the wave?
That last reference that I mentioned, the two paper, or the paper and patent, have some discussion about specific type of bullets, and sometimes they have to make certain assumptions about what the bullet is, because the shock wave does not only have one shock. It has a shock from the positive displacement in front of it, and then it has a negative. I mean, you have an N wave, essentially. So you have at least two shocks, and every irregularity that you have on the body of a bullet creates another minor shock. So essentially, there is some discussion about different caliber bullets.
Tony, I have a question about, you know, the sniping activity also. What if you have both the sniper and the detecting device, whatever it is, moving? Can you now detect, how many parameters you have to have in order to tell where the sniper is? And not only that, if you can do it, the direction and velocity that the sniper is moving in.
Yeah, in one of the brochures, and actually in the talk, let's say, one of the slides mentioned that, well, I've seen actually two numbers. One of them says that the vehicle can be moving up to 6 miles per hour, and still you have a good detection. And another one said 30 miles per hour. So I don't know which one, but definitely as long as it's not, you're not on a supersonic plane or something, which will have other signal to noise ratio. The typical vehicle in a cross-country environment is moving slow enough that it's not bothered by the speed of the vehicle.
Yeah, I was asking the question particularly when they were showing the moving helicopter.
Yeah.
Helicopters picked up the, you know, the source and everything like that, and said, well, yeah, but the helicopters moved. Well, but the computer can tell you where that sniper was, so then you can hone in on where it is. But I'm thinking, okay, well, the sniper. Now, the sniper, if I'm a sniper, I'm going to know all this. So if I don't want to get caught, I'm going to maybe shoot once and then move somewhere else as quickly as I can. But if you say, if you can tell within, you know, 6 miles or 30 miles an hour, that's fantastic. But the geometrical parameters have got to increase quite a bit in order for that to be put into a computer system, it seems to me.
Yeah, I mean, I imagine that most of these things, when they estimate, let's say, the axis of the cone or the center of the sphere, they give you, coordinates on the global system, so that if all of that is in your computer, you know how to train things, even though your own platform, the detecting platform, has moved somewhere else and has changed its bearing.
Tony, I read someplace a while ago, some marksman or sniper or something set some sort of record for hitting a target over a mile away, you know, with some sort of, you know, super duper gun of some sort. Are these systems effective for something like this, or is there a practical range which they become ineffective?
Let's say the only parameter that was mentioned in one of the PDFs that I saw was that the system works up to 75 meters, I think, when the sensor is up to 75 meters away from the trajectory of the bullet. Because after that, even the shot cone starts getting weaker, let's say, and yeah. But that was one figure that I saw. It didn't have to do with the range from the vehicle. It had to do more with the distance from the path of the bullet. If it was supersonic.
So if the bullet is supersonic and it travels, say, hundreds of meters,
Yes.
you still can do the math to figure out where the initial the rifleman or the person is.
Yes, I think actually the effect, are you now worried about the fact that gravity there will eventually attract the bullet towards the ground, therefore we don't have a straight line? The effect that has been described as more relevant in that paper that I mentioned is the slowing down of the bullet, which makes the cone have a sharper and a less blunt tip.
Yeah, and clearly gravity has an impact over long distances as well.
Yes. But again, if you think of it as typically in most of these displays that you see, it's a bearing and it's 1 hour wide. So you know the general area where the fire is coming from, but it's never going to be within a square meter unless you really have many of these systems and very quiet environment, and you don't have all of the things that become noise to the signal processing task.
Yeah, understood. Anybody else have anything? Questions?
Yeah, I got one crazy question. I'm thinking here of the opposite. I'm always thinking the other side. Has any of this research and development changed the design of any of the large projectiles? The bullets, I don't know because they're very small, but for flying through the air with a minimum friction, et cetera, et cetera.
Actually, I don't know, but I would guess that not much because these were primarily designed to take care of problems like Juba,
Right.
the guy that I showed earlier. I mean, yeah, for mortars or RPGs and things like that, it's a different problem, even though it has similar damaging problems,
Right. I was just curious,
Tony, I have a question. Is there a situation where somebody could coordinate multiple snipers in multiple areas?
I suppose that's what is that similar to the previous question, essentially? Yeah, you can have multiple snipers potentially, but assuming that they can all fire at the very same time, like with a GPS kind of time, those cracks will be distinct, that they will be picked up separately.
And even if they do fire,
I don't know the limitation, namely how close can they be before they become somehow an impossible problem to solve. I don't know that, but as long as they're far enough, and I would say, in terms of our response to sounds and microphone response to sound, where they can be talking about milliseconds or even in some cases, let's say fractions of milliseconds. They can distinguish much sharper pulses than our ears ever can. And when I say distinguish, I mean discriminate, because to us, 10 rounds fired closely to each other may sound like one very loud one, but to a microphone, they will have different spikes.
and even if the
even if you had a group of snipers with calibrated clocks and fired at the same time, the target would not be an equal distance from each.
That's right.
So that the system would pick them up separately. Now, the question that I had also is, have different kinds of sound discrimination been built into these systems, so that they can tell whether just from the nature of the sound, say the shape of the sound wave or something like that, whether it's a cherry bomb or something like that, or
I don't know the answer to that for sure, but I'm guessing that would be a matter only of how big a memory you can have, so that you can have a lookup table and do whatever is needed to do some comparison and the best curve fitting to the waveform that you receive. So, no, I don't know the answer, but I'm guessing that's possible.
Do we have any anecdotal, accounts of these things actually working and helping somebody out in a convoy or whatever?
Well, that BBC video that I showed, the guy was saying that essentially they made a difference in it, even though they were installations. They were not kind of people moving through the countryside. But do I have anecdotal? Do I have any direct? No, I don't have anything direct. I heard with my own ears. No.
Well, I thought it's the kind of thing that the PR division of the Defense Department would be happy to circulate, and I wondered if there were any stories. But
or sometimes they may want to not circulate it because, essentially, if it's a very successful thing, it may cause the other side to be much more cautious. I don't know.
If it's a very successful thing, the other side will become more cautious.
Or may become more inspirational to try and duplicate the same thing, to try and do the same thing, because they'll realize that it's possible. If they come up with a laser that can destroy a weapon at 5 miles distance, and they let people know about it, or if they have faster than light travel, and they let people know about it, it might not be to their military advantage.
Tony, just a question on the stuff that was presented. In most of the demonstrations, when they were in what looked like urbanized areas, there was line of sight between the shooter and the receiver, the microphone or whatever it is. How do you handle echoes in terms of secondary sound sources?
Well, you ignore the second. You try to work with the first arrivals, because in an urban environment, you'll have what eventually will be called a reverberant space. I mean, if you fire a shot and it's going down Fifth Avenue, the muzzle blast will touch all the buildings, right and left, and eventually at the other end, instead of a very well-defined, I would say, spike, you'll have a very broadened one, which is the superposition of the initial, of the direct shot, as well as the multiple reflections you'll get from each of the buildings. So unless that first shot is very well ahead of everybody else, it becomes difficult to do that.
Yeah, I think that's been, the stuff that I've seen in the paper from time to time with these shot detectors that they have in some urbanized areas for the civilian use. It's, they can tell you where it is in terms of like within a block or something like that, a very gross area, but they can't get it any closer than that.
I would say, that's correct and consistent with some of the things that I see, where essentially for the law enforcement systems, they require multiple sensors. I mean, it's a good product to sell, I mean, the more of these you put, the more accurate it will be. But ultimately, it tells you where there's an ongoing problem, basically. That's the value. The initial damage is always water behind the dam somehow. So it's that's the difficult part of this whole thing.
That was really a very, very good presentation.
Yeah.
So Tony,
Thumbs
thank
up.
you very,
Yeah.
thank you very, very much.
At the old Barnum and Bailey Circus, they had a man who was shot out of a cannon. And when he decided to retire, they had difficulty finding another man of his caliber.
One of the definitions of a physicist, it's somebody who multiplies 2 times 2 on a slide rule and he gets 3.8 and says, well, let's call it 4.